Okay, so we are going to look on something quite, I think it's beautiful. And in short, just on the saying that if the kernel, the null space of a matrix, and it doesn't matter if the matrix is square or rectangular, it doesn't matter. If the kernel of a matrix, and the definition of kernel is right over here, kernel of a matrix A is all the vectors from the space it's going from, such that if we are doing A times the vector X, we are getting the 0. So all the vectors that by going from using the transformation transform to the 0 vector. This is the kernel. So the claim is that for every matrix, again, doesn't matter if it's square, doesn't matter if it's rectangular, that the kernel is just a 0 vector. So we can say confidently that the matrix is, or if you want to say the linear map that is represented by the matrix, but let's call it just a matrix, okay, is injective, namely it's one-to-one. Let's see why. So let's start with the definition. Here we have a linear map A from V to W, and let's call it again just a matrix. How we define a injective one-to-one? If I take two vectors and I apply the matrix or the linear map on them, AX1, AX2, if this we conclude from every two vectors x1 and x2 from where we are going from, the vector space we are going from, that if the image of each of them is equal, saying means that x equals y, if this holds, so the maps is injective. It's like in functions when you say that fx1 equals fx2 means that x1 equals x2. This is exactly the definition of being one-to-one, namely injective. So it's the same as saying that the solution for ax equals 0 is just a 0 vector. When you see why, if we are saying this, so the solution to ax equals 0 is just a 0 vector, we'll just in a minute see why this is, if this holds, so the transformation, the linear map, the matrix, whatever you say, is injective. So again, the kernel, this is definition, all the vectors that going throughout the linear map to the 0 vector. So if the kernel is 0, it means that this holds every vector, or if a vector going using the map to be the 0 vector, it's the 0 vector. Remember this, very important. We'll use it now. So if the kernel is 0, namely this, the only vector that goes to the kernel is the 0 vector, this. The only vector that applying the matrix equals 0 is the 0 vector. This means the kernel is 0. So if we are letting, let's look at the definition of one-to-one injective. If we are letting ax1 equals ax2 for any xy and x1 and x2 in the space, so I can move ax2 to the left, getting this one, and equals 0. Now, because of linearity, I can say that it's a linear map. I can say that it equals ax1 minus x2, but it equals 0. But what we say is the only vector that equals 0 for a linear map that its kernel is 0, namely applying this, it's the 0 vector. So this must be the 0 vector because the linear map takes it to the 0 vector because the kernel is 0. So it must be that this is 0. So x1 minus x2 must be 0. It means that x1 equals x2. So what we've got that for any two vectors, x1 and x2, in the space, if they are equals, it means that they are the same. And this is exactly the definition of injective, of one-to-one. And this is why for every matrix, every linear map, doesn't matter if it's square or not, if the kernel is 0, this map is injective, is one-to-one. Linear map, because I use the linearity. Yes, so let's say this is the linear map. It means that the linear map is injective, is 1 to 1. Very nice, very nice. Kernel equals 0 of a matrix means that the matrix is injective, 1 to 1. Very nice proof. Thank you very much. If there are any mistakes or correction, please tell me. And that's it for now. And of course, thank for GPT for ordering and writing this very beautifully for me.